So now let's start with our discussion of WKB approximation method. This method is also called semi-classical approximation method. And here the WKB stands for three different scientists, Wenzel, Kramers and Brilliant, who developed this idea. And this is one another approximation method for solving time independent Schrodinger equation. So useful for solving time independent Schrodinger equation of slowly varying potential. So time independent Schrodinger equations of slowly varying potential. That is the place we are going to use WKB approximations. And mostly we will be discussing or using this method for solving one-dimensional problems or higher dimensions which can be reduced into 1D problems, or higher dimensions reducible one D problems. Okay, so before going further, I have to give a brief idea what is a slowly varying potential means. So let us take a potential like this. This is my potential v of x with x. Okay, so at any moment the energy of the particle is, let me take it as E. So it's a bound state, and if the moment the particle is there somewhere here, it is having a potential energy v of x, and whatever remaining energy that the particle is having is in the form of kinetic energy. And as you come up the hill, the kinetic energy component will be reducing because the potential is increasing, and finally when it reaches this boundary, your potential energy is going to be the total energy of the particle, and there is no kinetic energy. So what about a point here? Well, at this point we should have a negative kinetic energy, so that is classically forbidden. So this is actually, on any potential energy diagram, this is the classically allowed region. So particle will be moving from here and here. We don't have a negative kinetic energy in classical mechanics. Unless you have that component, you cannot have an energy which is coming down and the potential energy is more than that. So this is a classically allowed region. Okay, classically allowed region, and these are forbidden regions. Forbidden region, and this point is called the classical turning point, because at this point what will happen for any particle, the total energy is going to be the potential energy, and that means the kinetic energy is going to be zero. The particle is at rest here, and if the particle is coming from here, it will reach finally at zero velocity, and it will return back. So that's a classical turning point. Okay, something that you know already, I just wanted to briefly tell. We will be using it later on. Now, what is a slowly varying potential? How do you define slowness of this potential? So we'll use quantity which is familiar for you, lambda, the de Broglie wavelength. So any particle whose de Broglie wavelength can be calculated by using this expression h by p. So what is the momentum of the particle at any instant over here? So how do you calculate that? Equation for momentum is nothing but root 2m e minus v, or if you are taking the parametric form, it is nothing but v of x. Okay, so if you put that value here, your lambda will be nothing but h by root 2m e minus e of x. So if you know the energy, potential energy at an instance, this lambda at that instant can be calculated. It can vary depending upon x. So at an instant, if I calculate this lambda, I'm calculating this lambda corresponding to this point, for example, and I got my lambda value for a particular problem, this much. So this is my lambda. Now I'm comparing that lambda with my potential. You can see that over the length of this lambda, the potential is more or less constant. Right? There is no drastic change over the interval of this lambda. A slight variation for the potential, which is you can take it as the potential is constant over this interval. Or if the lambda is even smaller, you'll be having multiple number of lambda which covers over this kind of a constant potential region. So in that case, we'll call this as a slowly varying potential, because the potential is kind of constant over your de Broglie wavelength kind of a separation. Now suppose the lambda value is something like this. My lambda is so big compared to this potential. So in this case, the potential is varying in significant manner within the de Broglie wavelength, and this approximation is not valid in that case. So we want any case where this de Broglie wavelength or your potential is kind of constant when you're over this de Broglie wavelength. This is something that we are interested in. And this is actually true for all the classical problems, because when you're putting any, let us calculate, for example, a ball is being thrown, a ball of 1 kg is being thrown with in the gravitational field, or and you can just calculate the energy, potential energy, all those things can be calculated quite easily, and you'll substitute the value of the momentum, and okay, if you calculate the momentum, you'll be able to calculate this de Broglie wavelength corresponding to that, and that will be very small. And for classical problem, this is always the case, but quantum mechanically it is not. So quantum mechanically we have to put that fact explicitly for applying this WKB approximation. Okay, so this is actually the reason why we are telling this. It's a classically obvious thing that we are taking, but quantum mechanically it's not obvious. So that is actually the name semi-classical approximation has come. It's actually partially taking the result from classical mechanics or classically valid, take as our initial assumption for solving this problem. That's where the semi-classical approximation name came from. So okay, now let's develop the formal discussion of this formalism. Okay, so what we have to do is we have to solve our time independent Schrodinger equation, that is nothing but h cross square by 2m del square plus v of x into the wave function psi of x. Okay, I am taking one dimensional problem only. There is no need to discuss the general case here. We can just go ahead with the one dimensional problem in the case of WKB. As I suggested, indicate that is one dimensional. Mostly we will be applying it for 1D cases. E psi x. Okay, now we have solved this kind of an equation. Only thing is that we have taken in that case the potential as a constant one. Our particle in a box, we have a potential that is not varying, but a constant potential. So what was the solution for that? We just have to get an idea of this psi of x first. What is kind of the functional dependence of psi of x? To get that, we can just obtain, we can compare that with the constant potential formalism that we have done earlier. So this equation we have converted. Okay, I'll write it in 1D form. It's nothing but d square by dx square of psi of x plus 2m e minus v of x divided by h cross square will be the into psi of x is equal to 0, and as long as this term is going to be constant, uh, positive, you are going to have a sinusoidal solution for the, if it is negative, if v is higher than e, then you will be having an exponentially decaying solution, decaying or increasing exponential solution. Okay, so that was our general result for that. So general result for psi of x for a constant potential was, okay, that was for constant potential. For constant potential, we obtained the solution as something like a term a e raised to I. Okay, we have written it in terms of k by defining this as k. Right now I will write it as p by h cross. This is a p and h cross. So a e raised to I p by h cross. P is a constant here in this constant potential case, equal to v naught like that, plus another term e raised to minus I p x h cross. Okay, this was our solution for constant potential. Now what we have to see is what is going to be the change that the function is going to have when we have a change over this potential. Obviously we define it in the same way here. We'll take, okay, we'll write it separately and give an equation number d square by dx square psi of x plus, I am writing the top term as p of x square divided by h cross square psi of x is equal to 0, and this is my equation number 1. Now in this case the solution is going to have more or less the same form. Only thing is that the p over here is going to be a function of x. It's not going to be a constant, and depending upon whether the function is, it's going to be yeah, it can also have the position dependence over the amplitude. So that is going to be the general solution for slowly varying potential. So our solution is going to be of this form: psi of x, we have a which can have a dependence on x, and we have e raised to I don't know this functional form right now, so I'll take something like an s by h cross. That s is a function of x, so no need to write that x explicitly. It's going to be a function of x. Okay, so this is going to be my general solution for a slowly varying potential kind of. So what we have to do now is nothing but substitute this equation into our Schrodinger equation and obtain the result from that. So my Schrodinger equation is nothing but this. I need to calculate d square x by d square psi by dx square. So d psi by dx is going to be, I am not putting that functional thing, you just have to remember that it is having functional dependence. Okay, a prime e raised to is divided by h cross plus, you will be having 1 by h cross s prime e raised to is by h cross a of x also will be there. Okay, right? The differentiation of this component, it will produce I by h cross. S prime will come e raised to is h cross. Yeah. Now second derivative, d square psi by dx square is going to be double derivative of this one is a double dash e raised to is by h cross plus this quantity, if you differentiate, it will become, this is a prime, I by h cross, it will produce e raised to is by h cross and s prime plus that term is over. Now here I have ih cross. First I will differentiate this quantity s prime, then s double prime, e raised to is divided by h cross a. So here we have three terms actually. Now I will differentiate this term, that will produce me I by h cross square s prime square e raised to I h cross a plus another term, that is when you are differentiating a. So that will be I by h cross a prime s prime e raised to is by h cross. So these are the different terms which are there in that expansion. Now what else is there in our Schrodinger equation? P square by h cross square psi of x. So Schrodinger equation is nothing but adding this p square by Schrodinger equation is nothing but adding plus a p square by h cross square into psi of r. Psi of r means nothing but a e raised to is by h cross. Okay, right, yeah. So adding that term along with that will give you 0. This is what our Schrodinger equation is. Now what we have to do is we have to separate the real and complex. We have to separate the real and complex numbers separately, and then later you can write the coefficients directly equal to 0 because RHS is having 0. So identify the real components first. This is real, this is imaginary, this is imaginary, this is going to be a real, I square is there. So one real, anything else, this is imaginary, and this is also real. So three terms. Okay, so identify my real terms. A double dash. Okay, all these terms are having this e raised to I sh cross term. You can just remove that directly, no issue. RHS is 0. So first term only will be having a double prime, then second real term is going to be this thing which is having a minus sign, minus 1 by h cross square, right? 1 by h cross square, you have s prime square along with that, s prime square multiplied with the a. So that is the second term, and the third term is nothing but p square by h cross square a. P square by h cross square a. So these are the real terms identified, and imaginary terms all are having I by h cross. So I'll take that common outside. And what else is there? First term, a prime s prime, a prime s prime plus S double prime A, S double prime A plus uh, A prime S prime, A prime S prime again, so you can write it as 2 A prime S prime. Anything else? No. This is going to be the complete terms, which is going to be 0. So separately this is going to be 0, right? So for a modification purpose, I'll just multiply the entire equation with x cross square. Yeah, get rid of x cross square and later we'll substitute. So that will okay, and take a outside. So taking a outside from the first real part components and multiplying the entire equation with h cross square. So this term will be having h cross square a double prime divided by a, say I have taken a outside, minus h cross square multiplied, so s prime square, that's it, plus p square, h cross square multiplied and a taken, so this is nothing but p square. That is your first real part equation, and when you are multiplying this equation with h cross square, it will become I h cross. Want to take a outside, you can take 2 s prime a prime divided by a plus s double prime equal to 0. So you will get two equations when you compare the real and imaginary part. And how do we solve these equations?